This is Chapter 2 of Chem 102. This lecture, at least this portion of the lecture, will probably be at a faster pace. So let's start Chapter 2. What are we going to talk about in Chapter 2? Chapter 2, we talk about the air we breathe. What is air? And that will be a very important topic we cover. We'll be expecting you to memorize the composition of air. What are the components that make up air we breathe? How does the composition of air change from place to place? Because it does change from place to place, and we'll investigate that further. What are the impurities in air and how did they get there? Are there harmful components in the air you breathe indoors? Very important concept to think about and for us to examine and look at the chemistry that is and the science related to it. Are there ways we can prevent or limit contaminants from polluting our atmosphere? So that is what the Chapter 2 is outlined. That is the outline for Chapter 2, and let's proceed with it. So let's start with the first slide here. So let's take a look here at this diagram, and if you notice here, the troposphere is about 11 kilometers above the Earth, and that's where most of the air is, and that, again, this is where people inhabit and animals and plants are. Above that, we have the stratosphere, and in the stratosphere is a very important layer that protects us from UV, and that is the ozone layer, and that layer is very important. We're going to study that layer in detail. Then above that, we have the mesosphere, where you see what we call the shooting stars. So there's activity in that part of space, and that's the early part of space, or at least the near part of space to the Earth. Then above that, we have the troposphere here, and going up a little higher, 550 to 600 kilometers. We reached where the satellites are, and then we go into the exosphere, and that's where we go out of space and beyond. So, but the part that we are most concerned about when it comes to air, and primarily concerned about air, is in the troposphere. And so that's what we'll be studying in more detail. But as we talk about the troposphere, we will emphasize the importance of the stratosphere with regard to the ozone layer. So you want to hold on to that thought as we go throughout this course. That the troposphere, 75% of the air is where is 75% is, the troposphere is where 75% of the air resides or is, which is where people are. And then we have the ozone layer, which is the stratosphere, which protects from UV radiation. Okay, so let's move on. So you have those layers, you want to memorize them and be familiar with them. All right, the next one here is, let's look at this composition of air. It's very straightforward composition for the most part, except when we get into that 1%, the green area, as you see on this particular slide. So, the composition of air is a mixture, a physical combination of two or more substances present in a variable amount. That's what it is. Air is a mixture of compounds. It is a mixture, frankly, of pure compounds. But some of those pure compounds are what we identify as impurities because they have an adverse effect on humans, on people, for the most part. So we have the composition is about 21% oxygen, 78% nitrogen, then 1% of the other gases. So you want to hang on to this particular ratio again, about 21% oxygen and 78% nitrogen. The nitrogen serves as a diluent to dilute the oxygen, so that concentration of oxygen in the air is breathable for humans. That can and that is the comfortable, for lack of a better term, ratio that we have, or at least the ratio by which people and animals and plants and everything, breathing organisms, get to use for their biological system. So humans, so people, we use this, and actually animals do too, and plants use this. So air is 78% nitrogen, 21% oxygen, and all the breathing organisms get to take their air in this fashion. And then we have 1% of other gases, and we'll talk about those. So what do we breathe? Well, we breathe the following compositions. Again, air, shown the substance on the left side, is nitrogen. Nitrogen is the diluent. Oxygen is what we use to combust carbon species in our bodies, our Snickers bars and our candy bars and etc. We use oxygen to burn those and carbs and carbohydrates, etc., etc. And then we have argon has a fair amount in it, almost 1%. Then we have carbon dioxide at 0.04, and then water. Water is variable, and depending on where you are in the world, this is what changed the most in terms of air we breathe is water. So in an inhaled breath of air, we have that combination of 78% nitrogen, 21% oxygen, and almost 1% of argon, and then trace amounts of carbon dioxide. And then we're going to learn about some other species that are also there. And then we have variable water. So when it comes to that, the 1% argon and the 0.04% carbon dioxide, this actually is where some other impurities will come in as well. And we call them trace impurities, and you'll learn more about those. So you're taking this breath of air, deep breath, and you exhale it. When you exhale it, we burn, or we use oxygen to combust, to carry out combustion in our system. We call that respiration. So respiration, that means we take in 21% oxygen, but we only exhale 16%, and 4% of this oxygen comes back out as carbon dioxide. So what you know here is that the breath of air, so the composition of air we inhale is different than the composition of air we exhale, and that is the take-home point here. And that difference comes in the amount of oxygen and carbon dioxide. The amount of carbon dioxide increases as we exhale. That's because we have respiration that uses the oxygen and converts it to energy for our body, and we get to pump iron and things of that nature and get to walk around because our body is using oxygen and carbon species to generate energy. You will learn more about that in the chapters to come. So there we have it. All right. So that's what we breathe. So let's look a little bit further at thinking about this concept of air. What else is in a breath? Well, there are a lot more things in a breath of air. There are impurities. Okay. And when we talk about impurities, these are pure compounds that have deleterious effects against our bodies because of their chemistry. Follow? So because of their chemistry, they affect the way we breathe and the way we feel because our body cannot process those in a useful fashion. So this shows an image of what it used to be like in Beijing several years back when there was smog. The smog is what we call NO2, they're nitrogen oxides, and we abbreviate those as what we call NOx, NOx. So you hear about NOx and SOx. So a NOx is what's found in smog. So the brown color is because of the nitrogens in the smog. But after some years, many of the governments around the world decided that we would clean up our air, and what you see at the bottom picture is what Beijing looks like after air is cleaned up. So really, you really can see smog, and you really can see what we call bad air. And this is what bad air or impure air looks like, and we breathe this in. And when we breathe in the NOx are converted to acidic compounds, basically nitric acid type compounds, and those are irritants to our lungs and to our internal respiratory system. So in addition to nitrogen oxide, there are other colorless gases, and you're going to learn more about what those colorless gases are that contribute to air pollution. And this portion of NOx and SOx and other impurities fall really within that 1% of other that we show you on the previous slide. So we have this 1% of other, and that's where the NOx and SOx and other impurities come in. The composition of oxygen and nitrogen are almost the same. Water is variable, okay? And again, the other 1%, we have other materials, distribution materials within those. So occasionally, this bad air or this polluted air, or air with pollutants in it, or air with toxins in it, you'll hear these terms interchanged. These NOx and SOx, again, NOx gives us this brown color. This is smog. We'll find conditions where it will simply sit over areas for prolonged periods of time. And one way it does this is when areas are in valleys. These NOx cool air will bring it in, will trap this hard to breathe air, this bad air, in the valley, and it will sit there a bit longer. And if it's a metro city like Denver, Colorado, it sits there and it can really cause some problems for people who have breathing, breathing issues. Again, this is not picking on Denver, Colorado. All the cities in the U.S. and around the world have done a much better job in terms of how they clean the air. This example is simply for instructional purposes. So let's read the verbiage. Cooler air can be trapped beneath warm air due to weather conditions. Pollutants often accumulate in the cooler air of the inversion layer. In other words, what happens is the warm air rises, as you might expect, and that cold air traps in these pollutants. And again, it causes for smog and polluted air over certain areas. This situation is worse when the airflow is limited, such as cities surrounded by mountains, and that's a key point to hold on to. And so that's what happens. So this gives us very good reasons why we want to try to have cleaner air, and we want to be aware of the chemistry of the air and how we manage what we do as people with putting pollutants into the air, because they will affect us. And there's a principle that you will learn more about. It's a principle of conservation of matter. We can't destroy nor create matter. So once it's created here, it's here in some form, or we transform it into some other form. But once it's here, for the most part, it's here in some form. So we dilute it out, or we transform it into some other species that's less harmful. All right? So that's air inversion. Let's proceed on to the next slide. Okay, now, so how do we talk about these materials in the air? There are three main ways chemists and scientists like to talk about it. We like to talk about it on what we call a micro scale. That is the big scale. So if we take water, for example, the micro scale would be the water that's in your water bottle, or the water in your swimming pool, or the water that rains out the sky. We can actually see it, we can feel it, we can touch it, we can actually visualize it, we can interact with it, and therefore we call that the micro scale. Then if we take water, for scientists, we draw symbols such as H2O. Everybody's heard of H2O, but we're going to talk more in detail about it. You're going to learn much more about it. We call it H2O. That's 2 units of hydrogen. As we read these, we read from the right up in terms of the number of atoms or the number of molecules of these. So we have H2O, 2 units of hydrogen and 1 unit of oxygen. We don't write the ones at the bottom. This is how we draw the symbol. Then we try to picture this in a bit more of a 3D fashion so that we can actually talk about how the chemistry performs and how the chemistry interact and what are the key features of this chemistry. And we talk about that on a particular scale. And so these are particles, and we look at these particles, and we know these particles have 3D structures that allow them to interact. And there's a certain way they interact because of their particulate because of their particulate structure. All right. So we know that's how they interact. So let's read the verbiage. A molecule is a fixed number of atoms held together by chemical bonds in a certain spatial arrangement. In other words, we have exactly H2O that's actually bonded in a very specific way. The way water bonds is what we call in a bent structure, which you will learn more about. But it has a particular bent structure that allows it to have certain chemical properties. Okay. Keep in mind also, if you see bold, these are definitions that you will want to memorize for my class. Okay, the chemical formula symbolically represents the type of number of each element presented. H2O is 2 units of hydrogen, 1 unit of oxygen. Chemists use these 3 viewpoints to study, understand matter: microscopic, the very large scale; interactive scale, you can see it, you can touch it, you can feel it; symbolic, something we can write to help us think about the chemistry and the science of it; and particulate, we really are looking more 3D and how these molecules really are set in space, and what's the spatial arrangement of them, and how they really look, and where the electron densities of these are, and things of that nature. So that's how we visualize these molecules. And again, in air, we have nitrogen. We visualize it in all these ways. We have 21% oxygen, 78% nitrogen, and 1% of the other, which argon. And we look at all of these molecules in this fashion. So here's another picture of how we look at molecular structures. The particular view of matter shows a 3D molecular structure with atoms color coded. And these color codes were defined by this particular author or by really convention. A lot of people follow this convention. If you had invented it, you would have used a different color code. But this is the one that this author has adopted, and we tend to use this as a color code for us. So we are all accustomed to and can actually use a similar system. So the color code is magic, except that it's defined. Okay, I am not asking you to necessarily memorize the color code, but I am asking you to recognize that when you see it, we recognize that in this particular example, we have two units of the same atom and one of a different atom. And when we check the color code, we notice that the red is for oxygen and the black is for carbon. That means we have carbon with two oxygens, which is carbon dioxide, CO2, dry ice, or it's the smog you see at the concerts. Okay, you go to a Beyonce concert or Toby Keith concert or whatever concert you go to. If you see smoke on the stage, they use CO2. So this shows that depiction of it. So when we talk about naming these compounds, we have a set way of naming them. Prefixes are used to designate the number of each type of element. And these are the prefixes that we expect you to know. We will not sit here and read each of these in detail. We will expect you to take a look at them and know what they are, 1 mono to 2 di, all the way to 10 deca. So you'll want to be able to know that these are the prefixes. So when we talk about one atom, we would call it mono. For example, we would call it monoxide. Each of these is used to name the compounds, right? So, for example, carbon dioxide, that means carbon with 2 oxygen. Carbon monoxide, that's carbon with 1 oxygen. Then so on and so forth. With tetra, we'd have carbon tetrachloride, which would be carbon with 4 chlorines on it, so on and so forth. And we will expect you to learn how to name these by what we call binary compounds, bi meaning 2. So this means a compound that's containing more than one element from the periodic table. You studied periodic table in chapter 1. Again, this lecture is moving at a faster pace than would be with the live lecture. Naming binary compounds from nonmetals. We have prefixes that are used to designate the number of each of the elements, and we will go over these in work sessions and in recitations, and we will actually work through these independently. In the lecture, we will actually walk through the lecture, and then we will work on these in a different session. Sorry. Here we have N2O, which is dinitrogen monoxide, also known as nitrous oxide or laughing gas. And then the next example we have is diphosphorus, 2-phosphorus pentoxide, meaning 5 oxygens. And this is exactly what this compound is. Diphosphorus pentoxide is exactly P2O5. Dinitrogen monoxide is exactly N2O. And this is how we name the binary compounds. We will be practicing how to name all these binary compounds in different sessions and in our homework sessions. Hydrocarbons are compounds containing only a carbon and hydrogen atoms. We will talk about hydrocarbons now, and then we're going to return to this in a later chapter when we talk about fossil fuels. But for now, we just want to expose you to it, that hydrocarbons, organic chemists, have their own unique way of naming these compounds. And this is based upon that convention of organic nomenclature. We will certainly expect you to know what C1 is, which is methane. Again, it's gas. Okay, it's be natural gas if you would. We will expect you to know propane, which you use for barbecues. Butane is used in cigarette lighters. Then we expect you to at least know octane, which is what you have in your fuels. So we will talk as we go through which of these we expect you to memorize, but we would like for you to expose you to the number of carbons and the compound names, and it's advisable that you learn these, that you learn each and every one of them as we get going here, okay? So it'd be good to just go ahead, get a head start and memorize these, because you will see them again when we talk about fossil fuels. All right, air pollutants, risk assessment, a very important process is carried out. When it comes to risk assessment, it's evaluating scientific data. Notice that scientific data and making predictions in an organized manner about the probability of an occurrence. So in other words, we look at the data and we say, based upon these data, do we think there's going to be a problem with this material or with this compound, okay, or with this composition of air? And we make that decision again based on scientific data. We don't walk out and say, I think so. This might be a problem. We base it on the data. So to base the data, we look at two key components. That is toxicity, which means intrinsic health hazard of the substance. Each material has an intrinsic health hazard. Some health hazards are so low that they don't have an effect, so we call them, they have no known health hazard. Exposure is the amount of the substance encountered. So you can have something with a known health risk, but if you're not exposed to it, it's not a risk to you. So when we do the risk assessment, we know, for example, carbon monoxide is the silent killer, okay? And we know that it's dangerous. We know that we avoid heavy exposure to carbon monoxide. But if carbon monoxide is produced 100 miles away, it has no immediate effect upon us. If high concentration carbon monoxide is introduced in a closed system within our proximity, in a closed room, in a closed container, then it will have an effect on us. The toxicity would then impact us. So the risk there would be a high risk, low risk if it's far away from us. All right. So here we talk about evaluate the risk of breathing the amount of ozone in the air between the hours of 4 to 6 p.m. where you live. Note that you can go online to assess information about this. But what we like to point out to you is that when ozone is in the troposphere, it's called a secondary pollutant when it's in the troposphere. But when it's in the stratosphere, it is a protective layer for UV rays against the Earth. Okay, it protects the Earth from UV rays, and we'll talk more about what those are as well in other chapters. So one of the things that scientists like to do when we talk about these areas, we like to know what the concentrations are, and each area of science has its own unique ways of talking about the science. And here you're going to see how we talk about concentration conversions. So when we talk about conversion, because these concentrations are so small, scientists prefer to talk about them in what we call part per millions, part per hundreds, part per thousands, etc. So when we talk about this, 21% means 21 parts per 100. So if we have 100 parts, 21 of them, and 21 of them are different, if you would, then that would be 21% of those different parts. Okay. But if we put that in parts per thousand, that same concentration would be expressed differently. It would be 210 parts per thousand, or 2,100 parts per 10,000, and so on and so forth until we reach part per million. Part per million is a very popular way for scientists to talk about concentration. I expect you to know how to get to part per million. The difference between percent and part per million is a factor of 10,000. So essentially, if you know the percentage, you multiply it times 10,000 and you get part per million. I will expect you to know how to do that conversion. So percentages, to get to part per million, we multiply times 10,000. And so I expect you to be able to do that conversion in any direction. So let's look at these harmful few. Now you're going to see ozone show up. These gases represent the most harmful for our health and the health of our planet within the troposphere. So the most harmful ones within the troposphere, carbon monoxide. It is the silent killer. You don't smell it coming. It's odorless and it simply kills. It doesn't give you any warning. It just simply kills. If you suspect carbon monoxide poisoning, do not enter the area. Ozone is O3. So carbon monoxide is CO, by the way. Ozone is O3. In the stratosphere, it is a protective layer. In the troposphere, it's called a secondary pollutant for us, okay? It's been described by some as having a bleach odor or a bleach effect or a bleach smell. That's what you hear when people talk about ozone. Sulfur dioxide, SO2, which we call a SOx, and nitrogen dioxide, which we call a NOx. So we have the SOx and the NOx. The SOx, these produce acid rain, particularly SO2. So SO2 is when it's contact with moisture, etc. It produces acidic rain, acid rain, sulfuric acid, which is battery acid, NO2, nitric acid, which is again harmful as well. So these two acids, and then we have these particulate matter, which is things like soot. Soot is one of the most harmful pollutants there is, and essentially it's like it's basically like breathing small particles of small rocks, extremely small grit or what have you, into your system, and that cannot be digested. It simply settles in your lungs. Okay, so particulate is the other danger we have. Okay, and when we come to particulates, the size of particulate matters in terms of what you breathe. That's why people wear breathing masks when they carry out certain operations and certain types of jobs, and also in some areas where there's a high particulate content, people will put on breathing masks to help filter out the effects. So there you have it. We expect you to memorize these materials. Let's talk a little bit further about ozone then. Ozone in the stratosphere protects from UV rays of the sun, and we will go into more detail on exactly which rays it protects and how it protects us from. So that is the role of ozone. So it's very important that we do protect the ozone layer. And by the way, there is a hole in ozone. That is not a government conspiracy. That is not a bunch of quacks saying that that's the case. There is a hole in the ozone. We can measure it, and we know it's there. So that is an argument that you will not win in this class or with any credible scientist. There is a hole in ozone. The troposphere. Within the troposphere, ozone is called a secondary pollutant. Again, it protects us in the stratosphere, but in the troposphere is a secondary pollutant. And a secondary pollutant are not produced directly, but as a product of interaction of two or more pollutants. In other words, what happens when the ozone is in the troposphere, it interacts with other pollutants and other species, and that creates a secondary pollutant, and that causes us problems. So many times it's not the direct material, but as a result of that material interacting with other pollutants that causes a problem, and that's what happens with ozone. So it pollutes less at night because there's less sunlight to promote the reaction. In other words, we have ozone and these other species in the air. Sunlight hits them, it cracks them into these very highly energetic species. These energetic species collide with each other, and it produces these other species that affect our environment and affect the air that we breathe. You will learn more about what those species are and how that happens in this class. We also know that ozone is higher in the metropolitan areas because of higher emissions. That's what happens. So in metropolitan areas, very large cities, we get more ozone. And in fact, in metropolitan areas, we get more pollutants, period. That's what happens because of manufacturing more vehicles, machinery. Machinery is a big part of the pollution, is a big part of what pollutes the environment and pollutes the world. Okay? If it's mechanical, and particularly if it burns fossil fuel, it can cause pollutants to go off in the air, and particularly SOx and NOx. So here we show you some standards, ambient air standard quality. I don't expect you to actually memorize these values, but I want you to expose you, no pun intended, to what it looks like and how to read it. And what we look at here is the U.S. ambient air quality standards. We have the pollutant, the standards in part per million. Recall the part per million we talked about. So you know how to convert these to percentages by dividing this by 10,000, and you can see what percentage it is. So you can see these are very, very low numbers. Okay, these are out in the decibels. So, for example, in carbon monoxide, in 1 hour, the standard is not to breathe more than 35 part per million, and in 8 hours, an average of about 9. So this tells you where you want to be and what limits you want to be below, and the governments around the world set standards on all of these. And the real key take-home message here is that these standards are set, and that the more toxic the material is, the lower that standard is set. You get it? So we have lower values for things that are more toxic to us, And so these are the values that can be tolerated or we can live with and not have severe effects. Although for some people's system, these effects are different, and so that's individual. But on the average, overall, these are the standards for air quality, and this is what when the air is monitored, they look for these values to be there. Here we show you some good news that over time, if you notice the trend lines are going down, that's what we expect you to notice here. Air quality monitoring reports the average concentration of air pollutants in the United States has decreased dramatically since 2000. That's because many regulations have been put in place. You will learn more about what these regulations are. So you will learn more about what these regulations are and what they mean. So the real bottom line from here and the take-home message from this is that the quality of air in the United States has improved, meaning that the pollutants in the air in the U.S. have gone down, and these are all the ones they monitor and that they check. You know, we have carbon monoxide, the NOx, the SOx, the PM, those are particulate materials, etc. And another one here, PB, is here as well. This is lead also. Okay. This shows you we're not picking on any cities. This is straight from this particular author of research. He decided to do the number of healthy days per year in cities. Although air quality has improved in recent years, on average, people in some metropolitan areas breathe air containing unhealthy levels of pollutants, and these cities are aware of that. And you know, so from ozone, particularly pretty interesting, Boston versus say Los Angeles when it comes to ozone. So you can almost track this by size of the cities and industry and vehicles, etc. But just be aware of this, that it is different from city to city, and that larger cities and where there's heavy industry, there's certainly lots of automobiles and vehicles that are around a lot. The numbers tend to go up in terms of several of these pollutants. But it's pretty interesting how they control the particulates. So again, all this related to whether or not it's from vehicles or from manufacturing stacks. Okay. So here we don't see Detroit or anything on the line. So you might want to put Detroit probably somewhere around the Cleveland, Chicago type would be my guess here as well in Phoenix. So there you have it, or maybe in Pittsburgh. So there you have it. And then this slide, EPA air quality index is shown here. With this, there are color codes to warn people about how the air quality is doing, and depending on where you are in some cities, these are posted, and you'll see them on your news apps on your phone or on the television. And we show you the range here of what we expect, levels of air quality index, and these are indexes that are based upon the types of data that we've shown you on this slide. Again, the concentration of species in the air, particulates, and all these other things that monitor. And so these data have been put into classifying this as an index. And we show the index on the far left. And the colors are on the far right, or you can just see them as you look at them. If you have difficulty detecting colors, then you want to memorize the greens on the top and maroons on the bottom. And in the middle of this slide, we have whether it's good, moderate, unhealthy, sensitive groups. There might be people who have sensitivities to what they breathe, and there are people, and occasionally they'll have to wear oxygen tanks and masks and things of that nature to help them, and that's a good thing. And then we have unhealthy, very unhealthy, and hazardous. We will expect you to be familiar with this particular chart, certainly about what the colors mean on this particular chart, so we expect you to know them as well. So essentially the EPA has air quality index. We have these values on the left side that have been put together based upon the conditions of the air, the species in the air, the quality of the air, and from there the EPA has assigned these colors and codes to help people understand whether or not they're having a healthy day with air. And that will actually end part 1 of this lecture on chapter 2. Part 2 of this lecture was a live lecture that we recorded, and you can see that on the other videos.